Here's another short video on fluorocarbon polymers. Fluorocarbon polymers are very expensive, $5 to $27 a pound, but we want to look at them because they have outstanding properties. Exceptional lubricity, they are non-stick. Unparalleled chemical resistance, zero water absorption, and excellent thermal resistance. Certainly the most important of these is PTFE, polytetrafluoroethylene. Here's the repeating unit, CF2, CF2 taken n times. So PTFE constitutes about 90% of all the fluorocarbon polymer production. Take a look at this while I explain. So teflon was discovered about 1938 at DuPont when a worker noticed that a sealed drum of tetrafluoroethylene gas had lost pressure without a corresponding mass reduction. That is, it had no leaks. So when they opened up the barrel, they found that the gas had spontaneously polymerized to a white, waxy solid, which the gentleman here is showing his colleagues, PTFE. And because of its exceptional properties, PTFE grew to commercial scale production in 10 years, which is pretty remarkable. All the fluorocarbon polymers are made by the addition polymerization process using free radical catalysts and various organic and inorganic peroxides that we've discussed previously. In fact, even oxygen will catalyze the polymerization, which is very likely what happened in the case of the barrel that suddenly polymerized from the gas to solid Teflon. These polymerizations are exothermic. The temperature must be controlled to avoid explosions, and the polymer is produced by bulk or emulsion or suspension polymerization in water. Very simple chemical process for producing this stuff, starting at the very beginning. Calcium fluoride, it's mined in the ground, it's called fluorospar. It's purified and dried and powdered and then mixed with sulfuric acid, liberates calcium sulfate byproduct, and hydrogen fluoride gas is drawn off a furnace. The hydrogen fluoride gas is then dried and reacted with chloroform, CHCl3, and 2 fluorines replace 2 chlorines, giving us chlorodifluoromethane in the presence of an antimony pentachloride and antimony trifluoride catalyst. This is one nasty stuff. I've analyzed it in the past. It's a black, otherworldly looking thing, but it works. And then that's further condensed, removing 2 more HCl to give us the monomer tetrafluoroethylene, which is then polymerized by free radical addition to tetrafluoroethylene, polytetrafluoroethylene. So PTFE properties, it's highly polar, yet it has no hydrogen bonding. Why? Well, because it has no hydrogen. It naturally crystallizes to more than 90% crystallinity, and thus it is a bright, opaque white material. It's not transparent at all. It has tight, strong fluorine to carbon bonds and makes it the most chemically resistant thermoplastic polymer. It's attacked only by few chemicals, such as fluorine itself, which is one of the most aggressive chemicals known, sodium in kerosene solvent, and some perfluorinated solvents boiling near 300 degrees Celsius. Yikes, that's severe. The tight bonding also accounts for its natural lubricity. PTFE has the lowest coefficient of friction of any solid material, which means it's the slipperiest. It accounts for its use in non-stick coatings, like in fry pans, or lots of applications in industry. The polymer has the hardness and texture of polyethylene, so virtually no structural capabilities. It's waxy, it's a low tensile strength, it's subject to creep, which is stretching under load, and even under no load when not stressed, it undergoes what's called cold flow. So a piece of this, a layer of Teflon left on a bench standing, will start to warp just on standing. So structurally it's virtually useless, but it has these other incredible properties. PTFE has unusually wide temperature surface range of plus 327 down to minus 100 degrees Celsius, where its stiffening temperature is. It has the highest dielectric constant of any polymer, which means it's the greatest insulator. So think of an application where you have a thermocouple or electrical cable that's going to be in a hot location. You need a good insulator, you need temperature resistance, you need dielectric ability, insulating ability. That's the material you want. It is non-flammable, but it does emit toxic and corrosive fumes when thermally decomposed, so be careful of that. Processing of PTFE is quite difficult. When it's molten, its melt viscosity is simply too high. It's too thick to be injected by handled by normal injection and extrusion processes. And so, furthermore, its melting point is very close to its decomposition temperature. So how do we handle that? It's a process commonly done as called sintering. This is done with powdered metals as well as with Teflon. I have pictures here with powdered metal. This might be aluminum. It could be actually silica. It could be zinc or a brass. But here this looks like it might be zinc or alumina, maybe even silica. It's hard to tell by the color. In any case, PTFE products are produced by powdered metallurgy technique. The PTFE powder is pressed into a mold. So here it's being pressed in a mold under high pressure and near its melting point. So only the edges of the powder will fuse together. Inevitably it leaves some voids. The process is called sintering. And simply contoured parts, meaning not complex, simple parts, the gaskets and O-rings, can be produced by this process. It can also be produced under high pressure with a ram to make rods and tubing. So if you want something that's porous or gas permeable, then you want sintering. Like, for example, this air stone in an aquarium is made of a silica that's been sintered. Here is a close-up, like microscopic pictures of sintered materials. You see it's not truly melted. The edges are slightly melted, pressed together, still porous. Here's a brass sintered filter that's sometimes used in something like a fuel line in an automobile to pick up dirt, but allows the fuel to pass. All right, the applications of PTFE, based on its characteristics, are pretty obvious. Chemical storage tank liners. We want chemical resistance, right? Laboratory containers. You can buy a variety of simple lab materials like beakers and SEP funnels and such made of Teflon if you need the chemical resistance. Liners for pipes, liners for valves and pump parts, again chemical resistance. Chutes. So in industry, if you have a sloped slide in which dry material has to slide down, you might want to coat the surface of that with a layer of Teflon. That's what we did at work, and it provided a very non-stick coating that nothing ever gets stuck on. Fabric coatings. Teflon coated socks are amazingly comfortable. Electrical wire insulation in ovens, as already mentioned. Emulsion and suspension polymerized beads of 0.5 millimeter diameter are applied as suspensions in oil to form non-stick coatings. Hence we have these Teflon fry pans, right? Polymer beads or powder is used in anti-friction additives in lubricants and specialty waxes. So here you see this is Teflon wax, PTFE, turtle wax. So it's got little beads of Teflon in it. This is Teflon tape. Some people call it plumber's tape. It's soft, flexible. You can wrap it around pipe threads to make a seal. And of course it has complete chemical resistance. The stopcock that you would find in a burette or separator funnel is certainly made of Teflon because it's slippery. It's also chemically resistant. Here's a variety of labware. The materials that are bright white, that would be Teflon. Those that are translucent are other fluorinated materials we'll talk about next. Here we see Teflon coated fry pans. And here's a dry lubricant that contains PTFE for lubricity, and if you need a chemically resistant suit, I'm sure you'd be quite safe and cozy wearing one of those. Alright, there are some other fluorinated polymers that are quite similar. So CTFE, polychlorotrifluoroethylene. So just imagine tetrafluoroethylene, CF2, replace one of the fluorines with a chlorine, and you have chlorotrifluoroethylene. It's sold under the trade name CalF, and I mention it because you may see it at work. I certainly did. So it's manufactured, here's hexachloroethane with HF, producing chlorotrifluoroethylene, which is polymerized free radical addition. Ultimately here is chlorotrifluoroethylene. Looks almost the same as Teflon chemically. Replacing a single fluorine with chlorine retains many of the properties of PTFE, which is good, right? It has great properties, but allows conventional processing because its melting temperature is significantly lower. Instead of 327 Celsius, it's down to 218. Its viscosity is lower. We can inject it into molds and dies. We can extrude it and make more complex parts. CTFE is second only to Teflon in its chemical resistance. It has low crystallinity. Unlike Teflon, it is atactic, and thus it has high transparency. So some of the parts made of CTFE, they're almost as clear as acrylic or polycarbonate. Almost. They're a little clearer, for example, than polypropylene, than Tupperware, but not quite crystal clear. Applications include, printed circuits, electronic computer terminal covers, tubings. This is like an example here. These are CTFE tubings and fittings. Chemical resistant labware, again, we've had a number of that at work. And low molecular weight polymers are used as lubricating greases and oils. Where the grease and oil can't be attacked by whatever's in the process, that's the way to go. It's expensive, but it's unparalleled. Other fluoropolymers. So here's fluorinated ethylene propylene copolymer. So here this is tetrafluoroethylene, and this is perfluoropropylene, and they would be copolymerized in an alternating copolymer. So what would that copolymer look like? We'd have PTFE copolymerized with perfluoropropylene. So this is a 3-carbon perfluorinated group. So there it is. That's the copolymer of tetrafluoroethylene and perfluoropropylene. Second largest production fluoropolymer. Applications pretty much the same as Teflon. So whether it's CTFE or CTFE plus perfluoropropylene, it's almost the same. Polyvinylidene fluoride. I want to bring this up for a couple of reasons. So here we are in our last organic course, and I'm talking about vinylidene. And in the very first organic course, I was telling you about vinylidene. So you need to remember the structure of vinylidene, right? Vinyl is CH2 double bond CH something. Vinylidene is CH2 double bond C2 single bonds something. So what's polyvinylidene fluoride look like? Well, CH2 single bond CF2 repeat. I mention this because it is the most efficient piezoelectric material. Piezoelectricity is the generation of electricity on deformation, scratching or bending it. So for example, on your gas barbecue, you press a button, you hear a click. What's happening there is a material is pushing against and deforming a piezoelectric material, which causes a spark. Just the force, the weight of it. Quartz will do this. If you bang a piece of quartz against another quartz, you'll find it creates sparks, but this is far more efficient. It's widely used in microphones, burglar alarms, and detection devices for fire. Polyvinylidene fluoride. So as an elastomer, remember an elastomer is a material that can be stretched to about 2 times its original length or return back to its original length. We need to then be able to cross-link these. We can cross-link with peroxides. One example is FPM rubber. It's a copolymer of perfluoropropylene and polyvinylidene fluoride. It's called Viton, and it's used, and I mention this because we used it so much at work. It's used as high vacuum greases for, say, for example, for your desiccators, and anywhere there's cryogenic equipment. It has tremendous chemical resistance, and Viton O-rings and Viton gaskets. And we'll finish with this. Take a look at the pictures I have on the next page, and let's draw it out how that would form. So if we had perfluoropropene monomer, plus vanillidene fluoride, that would polymerize to polyperfluoropropylene polyvanillidene fluoride. Polyperfluoropropylene polyvinylidene fluoride copolymer, aka Viton. And that should do it for fluoropolymers.